Rolling here. Okay, I'd like to introduce our next two speakers, Tanja Lange and Dan Bernstein of University of Eindhoven. Please tell me how to say that like a grown-up.
So that's Eindhoven, and he's also at University of Illinois at Chicago.
I was going to get to there, but thank you very much. And they're going to speak on the NSA crypto library and not about the fabulous other things that they've done in a long and storied history. Please give it up for the new history of cryptography.
Well, thanks. Applause before the talk is even better. So this is about the SALT library, and this is joint work between Dan, me, and Peter Schwabe, who happens to sit here in the second row. Hi, Peter. Good. What can people see? They can people, yeah. So crypto has been standardized since a while. So we have the AES, so that's a symmetric encryption system. We have RSA 2048, and we don't actually have any real way of breaking those. So even when you see like the leaks and whatever, there is no indication that even the spooks have any real handle on those. So there's a widely adapted, there's no idea of how we can do them quicker, how we can break them quicker. So this is established research, and how then can it be that we still have problems? I mean, there are implementations out there. People tell, don't roll your own crypto, use our crypto, so OpenSSL contains a lot of crypto. And why then can it be that we still see security disasters? Why do we see that there's still a complete failure of integrity and confidentiality?
We were told, by the way, to suggest a trivia question. Here's one that we don't know the answer to because the answer is so big it's almost uncountable. How many security problems were there in SSL last year, SSL and TLS? And apparently there's some sort of prize for whoever can come up with this. Sorry? I heard some suggestion. SSL is very safe, yeah. So, okay, what we've done and we're going to tell you about is this new SALT library, NaCl, so pronounce that SALT, which is aiming at understanding why things have gone wrong in crypto again and again and again and again, and fixing those things so that they don't go wrong in the future. If you want to pick up the source code and documentation, go to salt.cr.yp.to. And we should also say that beyond the core development team that was mentioned on the first slide, there's also been code contributions from various people. Won't read through the names. Main thing that SALT is trying to do is actually encrypt and authenticate the internet. So even though we say, hey, look at all the things that are going wrong with the crypto that's out there, and look at this SSL problem, look at that SSL problem, really the number one thing that's going wrong is people not actually encrypting and authenticating stuff. And so we want to understand, all right, why is crypto not being securely deployed, and how do we get it securely deployed? The main thing that we actually want to do to authenticate and encrypt data is send a message from somebody to somebody else. Like Alice has a message to send to Bob. And then what do they know at the beginning of this? Well, they have some sort of public key. So Alice has Bob's public key, Bob has Alice's public key. Of course, you need some sort of key exchange to set that up. That's not within the scope of this cryptographic library. It's a very important thing to get right, but okay, let's just assume for a crypto library that that's been done. And then Alice wants to send a message, that's what's called M on the slide, wants to send a message to Bob, and somehow using Bob's public key and Alice's own secret key, which nobody else sees, Alice converts that message into a ciphertext, something you can safely send through the network, and sends that along to Bob. And then Bob somehow converts that ciphertext back into a message using Alice's public key and Bob's secret key.
Well, sounds easy, and we said there are crypto implementations, so let's do this with our preferred library, not SALT, just some library. So what you usually do is that Alice is asked to generate a key because, well, you need a fresh key for each connection, she's told. So Alice sets up a random AES key, she encrypts every packet of her message of this little m, then she hashes the encrypted message, then she goes and tries to find this public key that she somehow has gotten already. She recovers the math from the wire format because, well, you couldn't possibly expect that the wire format is identical to the math. So then she's using RSA. She uses her secret key to sign the hash of this message. Then, we've now done the encryption, we have done the authentication. Now we should also make sure that actually Bob can read this because Bob doesn't actually have this AES key. So now we have to go and look at Bob's key from wire format, convert it back to math. Then we can encrypt to Bob. So now we have Bob's public key. We can now send Bob the encryption of the AES key, and we can send him the encrypted message, and all that once we've converted to wire forward. Well, there's also all the stuff like at every moment I need to allocate memory, I need to figure out are there any errors and so on. So this is why the internet is not encrypted.
All right, suppose you want to do the same thing with salt. Then you take your message, you take the public key that you're sending to, you take the secret key that you're sending from, so Bob's public key and Alice's secret key, and then there's the most complicated thing here is the N, the nonce, and maybe I could also say how big these things are. The nonce is the third line there, 24 bytes long. Now, the reason for a nonce, what a nonce means is a number used once, like a counter, 1, 2, 3, 4, 5. Or you can just generate 24 random bytes if you are comfortable with your random number generator. I think for most people it's easier to count correctly. The whole point of a nonce is if you're sending messages like yes, yes, no, no, and then somebody can guess what those messages are, if somebody sees the same message again encrypted as the same ciphertext, they'll recognize that repetition. And so if they happen to know what one of the messages is, and you happen to send the same message again, well, you have to make sure it's encrypted differently so that the attacker can't tell that you were repeating the message. And that's what that nonce does, is it makes sure that you're encrypting each message in a different way. And then all of these PK and SK and M and N and C, those are all string variables. If you're using the C interface, C salt, get it? C salt, ha ha ha. If you're using the C interface to salt instead of the C++ interface or the Python interface coming out, in C then of course the strings are pointers with a length variable attached, but the interface looks basically the same.
All right, so Bob, on the other hand, he receives this message, and now it's a box message, so Bob does box open. Very similar arrangements. Okay, now there's a ciphertext instead of the message. Bob also has received the nonce, this counter value. Just to add to this, you do not need to keep your counter value secret. It is okay if it's predictable. It just should not repeat. So it's not a secret. It's just something, well, don't repeat the same thing. And then his public key and, Alice's public key, his secret key, and then that gives him the ciphertext. Now, we're cheating a little bit. This is not the whole thing. At some point, they needed to set up the keys, but that's also just a one-line command. He says, well, here's a pointer to my secret key. That's where I would like to store it, and it issues you the public key. Now, sometimes it's not that you have a point-to-point communication, but you would like to sign something. You make a public statement, and you don't actually know for whom this public statement is. Say you go on Twitter and say, crypto is awesome, sign Tanja, then I need to be able to sign this in a way that next year somebody else can also verify it's by me. That's a different primitive from the box. The box, I know I'm sending to the person over there. So at this moment, I know who we are. With signatures, I have no idea who is going to verify this. So these are two different kinds of things. So we're also providing you signatures, which are for public messages. Well, they might also be in private messages, but then I could use the box thing, because the box thing also makes clear it's from me. Now, signature API looks very similar. There again, we have like a public key. The secret key is twice as long compared to the box version. Gonna get into that hopefully towards the end. And then we sign it and we open the signature.
Okay, you might say, hey, if these are all the functions, then that can't possibly be enough to do serious crypto, because if you have OpenSSL, we were thinking another trivia question could be, how many functions are in the OpenSSL API? I think even the OpenSSL developers have no idea what the answer is. I mean, how could it possibly be that you could have a crypto library where you can actually remember the API? And you might think, well, this is not enough for applications. But, well, the proof that it is enough is that there are applications which are actually built using exactly the CryptoBox interface. For instance, DNS Curve, DNS Crypt. This is doing authenticated encryption for DNS queries. Both of these are supported by OpenDNS. If you look at Google's TLS replacement, Quick, then that's using the CryptoBox interface. If you look at Ethos' new high security operating system, then that's got an even faster TLS replacement than Quick. Quicker than Quick, I suppose, called Minimalt, and that one's also using this interface, encrypted chat application. So you see that people are actually doing successful crypto for the things you want to do with authenticated encryption using this interface, and similarly for signatures. Lots of successful applications.
All right, so if you like salt, what you're hearing there, you want to see it and you want to use it, first of all, there is our webpage, the salt.yp.to page. There's also a packaged version maintained by Frank Dennis, and he calls it Libsobium, so it's basically the salt interface, just, well, his own version, it's on GitHub. Then we have a version which we call Tweet Salt for the obvious reason that it's a re-implementation of salt in 100 tweets. So you can go on our Twitter page. It's not a very active Twitter. I mean, not really much point in following us because the 100 tweets have been tweeted and the library is stable at this moment. We have written a little paper about it. What's the application? Well, the application is kind of, if you find yourself in a country where maybe Twitter is not censored, but you can't reach the salt.co.yp page, you can go on Twitter because who would be so cruel blocking Twitter? Or at least Twitter is little less strange to visit than some pages that Dan owns, and you can get it there. All right, but then you get in the whole thing in tweets and you have to kind of figure out how to make it look like normal code. But the nice thing is, when you make it look like normal code, it fits on a sheet of paper. Somewhat small font, but actually still readable. So like in the good old days, or bad days I should say, when the PGP was printed as a book and was carried across the border, you can now take TweetSalt on one sheet of paper, fits anywhere, and you can carry it across the border, then you have on the other end an OCR scanner, or you just retype the thing, and there you have a crypto library. This is a re-implementation, so it has the same API, same functionality as Salt. It's also nice for prototyping. It's just very small if you're one of those people who just cut and paste from the internet. Please cut and paste from here. Do not cut and paste from just somewhere Stack Exchange or random Google hit. So it has everything except for it doesn't have the speed. I mean, it's fun if you just want a prototype, it's there. If you want the full speed that we're going to show you later on, then you want the real Salt library. Speaking of speed, we are maintaining also a benchmarking project, so it's at bench.co.yp.to, and there we're benchmarking all kinds of crypto functions, so symmetric encryption and decryption, there's stream ciphers, there's block ciphers, there is public key encryption, there's hash functions. Now, the relation with these is it has the same API. So if you understand how this crypto API works for the Salt library, then you can basically also use all those functions. I mean, they're not implemented by us, so no guarantees or whatever. All the cool things we're going to show you in the next slides do not necessarily apply to those functions, but if you need other functions, there they are for download.
Okay, so what security features do we have? What's actually going wrong with the libraries that are out there beyond the API, beyond the usability? Well, there's lots and lots of problems. For instance, timing attacks against your load and store addresses. So here's an example of what went wrong. There was an attack paper in 2005, Osvik, Shamir, and Tromer, or maybe the paper's from 2006, but they announced it in 2005, which said in 65 milliseconds they are extracting the AES key out of the Linux decrypt encryption device. So the kernel has an AES key, which it's using to automatically encrypt stuff that you store on disk. This is still the situation today. And what they did in 65 milliseconds was, without breaking through any security holes, buffer overflows, or whatever, they figured out what that AES key was. Just by watching, well, not the outputs, that would be a serious attack against AES, but by watching the timings of the AES encryption process. So you have to look in detail at why this works, and fortunately there's going to be a tutorial tomorrow, so maybe I'll just skip past the, and also on the next page there will be a mention of when you get the tutorial. I'll skip past the detailed description and just say, well, there's reasons that timings of what's going on inside the computer leak the AES secret key. And then people in current libraries since 2005, in the last 10 years, people have tried to defend against this in various ways, which I think you'll also hear about in that tutorial tomorrow. Unfortunately, these ways, well, you can't really convince yourself that they're secure, and sometimes there's papers saying, no, they're not actually secure. So what we do in SALT, and what you'll also learn about, and I hope we're not loading too much on your tutorial tomorrow, what you'll also learn about in Peter Schwabe's talk tomorrow at 11 o'clock is how to protect yourself confidently against timing attacks. So how do you make sure that you just will not leak any secret information through timing? In particular, timing of the load and store addresses that you're using. Well, in SALT, we just make sure that we never put any secret data into any, if you say X bracket I, then that I is never a secret. So there's just no data flow from any secret data to any of the array indices that we're using.
All right, loading on security features. Also, if you have, instead of doing your nice table, you say, well, if my secret is 0, go right. If your secret is 1, go left. And even if, you saw that, right? You will also see this through timing, because the if waits for a moment when it's true, and then when it's false, and then goes to the else, or you go directly to the right side. So in Salt, we avoid completely to have secret branch conditions. This is actually a problem in reality. So Billy Bob Bromley and Nicolas Tuveri showed just a few years ago, 2011, that they could attack the OpenSSL implementation of ECC, so the signature version of elliptic curve crypto, by using the secret branch conditions, by saying, okay, go right, go left. And that was after they had started putting in some countermeasures. So it's generally a problem, and the mem copy is a mem comparison is a very typical case, like the old password check. You can see whether it's the first character that's incorrect, the second character that's incorrect, and so on, just by waiting for how long does it take till it says failure. We avoid that. So no branch conditions that depend on any secret data.
Okay, maybe for padding oracles, we've got a couple of slides on padding oracles that we'll just skip past this as well, because you've already heard a lot about it. Lucky 13 and Poodle. These are examples of padding oracle attacks. This is information being leaked through padding of data, where somebody who's sending you ciphertext can then figure out, you try decrypting something and checking the padding, and that leaks information, sometimes through timing, sometimes through other oracles. And this is something else where in Salt we just completely avoid the problem, but again, since there's been so much news about padding oracles, maybe just skip past that.
It's something where it's easy to avoid than to describe.
Yeah. Okay, here's a different thing, randomness. In particular, there's all sorts of problems from decentralized randomness. If you look at, for instance, the Debian bug, that's what it's typically called, for 18 months, Debian and Debian derivatives like Ubuntu were generating very little randomness in their SSH keys and all sorts of other secret keys. So few different keys, you could just run through like a million possibilities, and then you would find all of the secret keys that people were using. So real disaster. What happened there was that some developer had run a code verification tool on part of OpenSSL that was generating random data. And the code verification tool said, whoa, what's going on there? This code is behaving kind of randomly. Code shouldn't do that. And then the developer said, oh, there's a complaint. How do you get rid of the complaint? Guess we'll comment out this line of code. Oops. Now, you could say the problem here was just somebody who was paying too much attention to a tool should have been fixed, but we say that the problem here was actually that OpenSSL had randomness generation code in the first place. Because if you think about the whole software ecosystem, it's not just OpenSSL, it's everybody who thinks, oh, I need randomness, where are they going to get it from? Well, sometimes they'll get it from the operating system, this is what we do. We take dev urandom, and we take random data from that. If the kernel upgrades its interface to get random data, to, for instance, guarantee you have something initialized, that's good, we'll do that. So that's recently happened in Linux, but the default baseline that just works on lots of systems is dev urandom. Sometimes people do that, but sometimes people say, no, we know better. We can generate better randomness than the system. And so they end up writing their own code, and then there's 1,000 lines here, 3,000 lines there, which are collecting randomness somehow, and it's impossible to audit this. It's impossible to get it right. If you say the kernel or the hypervisor, one piece of code that everybody uses is generating randomness, then at least you have a chance of getting that right. When you have OpenSSL and every other library and every other program that thinks they can do better trying to do their own version of randomness, they will not get it right.
Now, of course, there are also bad versions. Let me click one more. There's also some advertisement where you hear from Intel that you should only use one source of randomness, namely their randomness. And in some sense, it sounds a little bit like what Dan just said. Well, look, there's one thing which has been reviewed really carefully by some closed evaluation labs, and you can, of course, trust them. Except for, there was a paper at CHES 2 years ago showing, so CHES is cryptographic hardware and embedded systems, where some university researchers showed that you could actually have taken the same silicon, but then changed the dopant level. So this is something where you do not see it under the electron microscope. You do not see any extra wires. The only thing that has changed is your silicon has changed from more positive to more negative in certain spots, which then meant it was actually implementing something else. And they were demonstrating by that you could have a backdoor there, which even if, what's the guy's name, David Johnson says, well, he looked at this as under an electron microscope, he wouldn't have seen it. So even if, honest to God, he believes that there is no backdoor, there could still be some backdoor. Now, we're not saying we're using, well, we're actually not using the Intel random numbers, we're using the centralized operating system random numbers. If your OS decided to use the Intel random number generator in there, it at least does so by mixing it in with all the other things, by hashing it through before using it, so that even if there's a backdoor, it can't do damage. So the merging is deterministic. What we're doing is we're taking from there, we assume that somebody has audited the Linux thing, unless, well, it hasn't happened, then maybe once we're done with fixing the crypto, we might move on to there, but that will take a little while. Anyway, so what's better than good randomness? It's avoiding unnecessary randomness.
Okay, so this was an example of another cryptographic horror story, although this is a case where I very much side with the attacker. Sony was being really obnoxious and turning off people's ability to run other OS under PlayStation 3s. And, well, Sony turned this off for no longer getting a tax break, apparently, for selling computers. And they said, oh, if we don't get a tax break, then, well, we'll just sell PlayStation 3s as game consoles and then turn off the ability for people to run anything else. And so this pissed off a lot of people, and the fail overflow group completely broke the ECDSA signatures that were used in Sony's PlayStation 3 security system. Fantastic talk recorded from the Chaos Communication Congress in 2010. Now, this is not a fundamental problem with ECDSA in the sense that everybody who implements ECDSA is definitely going to get this wrong. But there is this very serious trap that if you implement ECDSA and then at a certain moment you get to the spot in the algorithm that says, now take a real random number. Well, Sony did that. 4, yeah, okay, so 4, generated by dice roll, guaranteed to be random. Sony took a real random number and somehow they missed the warning saying every signature needs its own random number. So they kept reusing the random number again and again, and that completely breaks the security. Now, what we do is don't have randomness showing up except when you absolutely need it. And the one spot where you absolutely need it is when you're generating a key in the first place. But you do not need signatures where every signature needs its own randomness. You do not need the crypto box to have any randomness. Somebody has to put in a counter, or maybe somebody would want to do randomness as input, but the crypto library doesn't ever say, oh, I need to generate randomness to encrypt and decrypt and sign and verify data. So we just always have deterministic crypto box open, crypto sign, etc. This also means that we can test all of these functions, makes the auditing easier. You can check that everything is doing what it's supposed to be doing, except, okay, the key pair generation, that's the one spot where you absolutely need randomness, and that means focus more testing effort on that.
I mean, the keys were the 32 bits and 32 bytes and 64 bytes. So it's not much randomness, but yes, you should have that. The other thing, why are we writing this crypto library? Well, I mean, my usual head is I'm the cryptographer coming from mathematics. The good thing about having a cryptographer write this is that we listen to what's happening in crypto. We get the early warnings. So what's publicly known about MD5? Well, first, don't use MD5. For most people, the public history with MD5 started 2008 when Mark Stevens, Alex Soturov, and then Jack Applebaum, Arjen Lenster, David Molnar, and Tarek Özvik and Ben de Vera showed that you can come up with the CA certificate, which never was signed by the CA. Because, well, when you sign something, well, when the CA signs something, they don't actually sign the whole certificate, they sign what we call a hash, which is a short fingerprint of it. Now, this function taking the whole certificate and deriving this fingerprint, that was MD5 at that point. And MD5 has a property that it looks like it's really hard to get back or to find another one which has the same fingerprint. And, well, that's why people use it. However, for MD5, research has shown that, yes, you can come up with 2 different messages which hash to the same value. And they exploited this by getting this rogue CA certificate. And 2012, the Flame attack came out, which was also using a new MD5 attack. However, when you look back in the history, what the cryptographers will tell you, like, yeah, we knew since 1996 that MD5 was weak. Back then, Bart Pernille and Hans Dobertin were showing that there are some properties in these functions which they couldn't quite exploit to the full extent of going back or coming up with two different things. But for a very, very closely related function, which is something which like smells exactly like MD5, they could do it already in 96. Now 96 was just after this function had been proposed. It was not the, it's everywhere and we have to call in the Microsoft MD5 cleanup crew, which will be busy with this for years. No, it's just, well, 2 years into proposal, could have been easily removed if people had listened to the cryptographers. So we hope at least that we're getting the early warnings by being cryptographers, by going to the crypto conferences, and for the SALT crypto library, we have been listening to what's going on, so our choices are using our knowledge in cryptography.
Okay, so it's reasonably clear that from everything we've been describing, we're going to run into one really big problem. You make everything usable, nice simple packages, and then you have all these security problems where you just deal with them from the start and never do this, never do that, make sure to do things that way, put yourself under tons of constraints, then clearly you're going to have a problem with speed. So this is something where people using crypto very often make decisions on the basis of the performance of the crypto. For instance, here's an example which was going for many years. It was fortunately fixed in 2013, but Google, until 2013, was using 1024-bit RSA for all of their SSL servers. Now, this is, for comparison, something where if you look back to 2003 in the cryptographic literature, people like a paper from Shamir and Tromer, Shamir's the S in RSA, and Shamir was saying, okay, for something like $10 million and about a year of computation using 2003 chip technology, he could break 1024-bit RSA. And just imagine how much cheaper the same computation would be now. And as a result of this, RSA Laboratories and NIST said move to 2048-bit RSA before 2010, which for my taste is waiting way too long, but okay, that's what they said. Another example of people making decisions on the basis of speed, Tor also. People doing more serious crypto and paying attention to these warnings. Still, 2013, they were using RSA 1024, not RSA 2048, despite the years of warnings. And the reason for this was exactly speed. They eventually, 2013, they switched to Curve 25519, which we'll say just a bit more about. Third example, DNSSEC, still today, so the remaining examples here are things which are still using bad crypto because of performance. Bad crypto or, well, okay, no crypto is the worst case, but this example 3 is DNSSEC is almost universally, the things signed in DNSSEC are signed with 1024-bit RSA, still today. And explicitly, the documents say this is for a trade-off between the risk of key compromise and performance. Well, these keys are compromised by any serious attacker, but still for speed reasons, people are using RSA 1024. Fourth example, the timing attacks that we mentioned before and that you'll hear more about tomorrow if you come to Peter Schwabe's talk, if he finishes typing it. These timing attacks are something which you can still carry out against a lot of libraries out there. OpenSSL, for instance, on ARM processors still has secret load addresses where, well, they say there's some countermeasures and it's not obvious that it's breakable, but it's also not obvious that it's secure. And these things do keep getting broken, like Lucky 13 was partially a timing attack. Last example here, example number 5, SourceForge. Major open source distribution site. Okay, not quite as big as GitHub, but it's still one of the major players in people developing collaboratively open source software. If you log in for your account, then that's HTTPS. If you try to do the software development pages on SourceForge using HTTPS, they will accept the HTTPS connections. They've set everything up to securely redirect your browser back to HTTP. So now you have a clear text, unprotected, no integrity connection to SourceForge.
All right, so after seeing all these disasters, so what we have in there, so make it even harder for us, let's skip all the low security options. So first of all, we do not implement the null cipher. It would have been very easy to add, but we decided not to. We also don't give you much freedom. You get the box, well, there's a little bit that you can save, but the box automatically encrypts and authenticates. If you don't need the authentication, just ignore that value, but we make sure that you get an incentive to always authenticate. And as we said before, well, you check the authenticity before you check the encryption. We don't give you RSA 1024 because we know it's breakable. We don't even give you 2048-bit RSA because, well, who knows, plus it's kind of slow. So we're making it also a little bit easier for us by not going for the slow and old primitives. What we're doing instead is, well, yes, we don't want it to be too slow. What we're doing instead is, well, make it fast. Sounds easy enough, right? So we wanted Salt to be secure. We wanted Salt to have all the countermeasures in place so that timing attacks, branch prediction attack, hyperthreading attacks, and so on cannot get you. But still, Salt manages to keep up with the network for pretty much any value of network.
Okay, so here's some concrete performance numbers. This is not using some latest fancy expensive processor. Suppose you have a $200 AMD 6-core processor from 2011. It's not the absolute cheapest processor out there, but this is not.
One.
Yeah, I mean, we have one. It's one of the many processors that we benchmark on, but okay, just, some sort of middle processor that you might have in some cheapo servers. Here's how many of the operations we've described that processor will do. Every second, CryptoBox will be more than 80,000 operations per second. So think of that as 80,000 separate cryptographically protected packets. The CryptoBox open, similarly, more than 80,000 per second. The CryptoSign open, more than 70,000 per second. That's the signature verification. Maybe I should comment that the signature verification is something where, why don't we have a separate verify function? And why is there CryptoSign producing a signed message and then CryptoSign open, which is giving somebody, well, why don't we have CryptoSign, which says there's a message and then a separate signature of it? Why do we have that there's a signed message, which you then feed through CryptoSign open to get the verified message out? And the answer is, if there's a separate signature, which is the usual API, then suppose somebody just doesn't bother checking the signature, then they will have code that seems to work for all the normal tests, but actually they haven't checked the signature. And by having CryptoSign open be the way that you get the message out of the signed message, we avoid that kind of usage mistake. Anyway, so that was the verification function. That's more than 70,000 per second. And generating signatures, that's particularly fast, more than 180,000 signature generations per second. What does this mean in terms of speeds? If you have one of these CPUs behind a 10 megabit per second connection, or if you have 10 of these CPUs behind a 100 megabit per second connection, the CPU will be only a third loaded to keep up with that. If you have, say, 30 megabits per second for one of these CPUs, then that'll fully load the CPU doing this crypto.
Now, this is the speed, say, the CryptoBox open, if you're one server and you have lots and lots and lots of different clients talking to you. So every second there's, well, for every connection it's a different public key coming saying, hey, talk to me, talk to me. Usually you have longer lasting connections. Usually it's that guy over there who has already looked up Google and now wants to do the second Google query. He's still on Google. It's still the same connection. Or he logs into his Gmail and continues using the Gmail. So they only needs one time here is my public key, here is Google's public key, let's do the public key, the expensive part. And we recognize this, so instead of, I said before, well, we only give you those primitives, we also give you the possibility to jump in to this process and say, okay, we already have a shared secret. This is interesting, for instance, if you're running a server and you're scared of somebody DDoSing you, which means lots of new requests, then you can have a much smaller capacity process running, which is just serving the clients who are already there. So the speed on the left slide is showing you the speed for new connections, but if you have ongoing connections, then you're getting up to, say, a gigabit per second link speed. Just by saying, well, this is like the bulk encryption, this is your movie download. There we get the gigabit per second, and that's pretty much what we see on the internet at most. So that's then the pieces where the CryptoBox is cut into the before NM and after NM. So that's the before the public key and after public key.
Okay, some more speed features. If somebody's sending you these forged packets, then as Tanja mentioned, rejecting forged packets is something that you might have more capacity devoted to that and keep up your successful packets with the known users. But something that's particularly nice about this is that the forged packets are just using secret key crypto where quantitatively, I think you skipped the 1 gigabit per second number. This would be, suppose you have normal full-size packets, like somebody sending you, doing file transfers, say, or big connections, a typical big kind of traffic that occupies most of your internet traffic. Then that's going to be 1 gigabit per second for public key operations, and then it's much, much faster if you just get to do secret key operations. Last little speed up here is batch verification. So this is if things here are still not fast enough and you need even more speed, then what you can do is take a whole bunch of signatures. Suppose they've been piling up signature verifications that you have to do. You can actually grab a bunch of them and verify them all at once, something like twice as fast as verifying each one individually. And it's still just as secure doing that. If you only have one signature coming in, you verify that and don't wait for more, then you can't get the speed up. But if you're falling behind, then this is exactly what can save you and keep your server up with twice as much traffic.
All right, so it's up to me to advertise another project that Peter and Dan have been doing, namely getting the same library working on small devices. So we've been talking about, okay, slightly outdated, but still big CPUs. So the two of them also have Neon Salt, which is, well, Neon Crypto, which is the Neon version of Salt. So if you have the somewhat better version of the ARM chip, then it has Neon instructions, and their library is using this and gets pretty decent speed, also gigabits a second. So the timings are done on a Cortex A8, which is not really up to snuff nowadays. It's something like several generations of phones back. But even with that chip, which you can now get, say, from Allwinner in bulk for under $10. Do you have the prices? I'm sorry. $5 a buck. Okay, I didn't look up the latest price. So really cheap ARM platform, then you can get very good speeds on that with that library.
Okay, so saying, well, we've got all these security constraints and we really go for really high security and then at the same time provide this with really good speed. This sounds like a conflict, and this is why they pay us the big bucks. The actual details of what we did, okay, they don't pay us that big bucks, but you know, university jobs, they don't pay so badly. So what did we do here? What's under the hood? What makes things run securely at such high speeds? Well, there's a number of little decisions. First of all, we do not use RSA. This is one absolutely critical thing. If you want, I mean, people have already been turning off RSA because it's such a disaster for forward secrecy performance. If you want to have your connections not be decryptable for somebody who later breaks into your server and grabs your keys, then you have to be using forward secrecy, and it's just complete disaster with RSA. The whole model of CryptoBox, just take a packet and encrypt it, CryptoBox open, take a packet off the wire and decrypt it, that's something which you cannot do efficiently with RSA, especially if you go for a reasonable security level. Tanja mentioned that even 2048-bit RSA, not so secure. If you go to something reasonable, like 3,000 or 4,000-bit RSA, it becomes really painfully slow. Even 2048 bits, people complain a lot. ECC, we switched to, and along with getting much better performance, we actually have a much stronger security record. The funny thing, people know about RSA because it was the first important public key crypto system. It was introduced in the 70s. ECC was almost 10 years later, mid-80s. Now, it's taken a while for that to get into textbooks and for people to learn about it. But the funny thing that happened was, in the meantime, there were all sorts of attacks against RSA where those attacks do not apply to ECC. There's a whole attack strategy called index calculus. This is one of the things that we were talking about here last year. Index calculus is something that makes RSA look less and less secure when you go from the 70s to the 80s to the 90s and even more improvements in the 2000s. Whereas ECC is invulnerable to this attack strategy. So we actually are much more confident in the security of ECC. ECC has the security today that's very much the same as a security picture from the 80s, just the attackers have bigger computers, but it's not like there's all sorts of fancy, scary attack algorithms to worry about. And it's not that people haven't been looking for these algorithms. ECC is the obvious attack target at this point. So it really seems fundamentally stronger than RSA. You want to do the second one? Or, okay, I'll keep going on the slide. So another example, so this was also what we were talking about last year, was the main point of our talk last year was how do you choose curves to use in ECC? And this is a big ongoing topic of debate, and you can get a lot of the criteria from our webpage, safecurves.cr.yp.to. There's right now various people talking about exactly which curves that are declared to be safe here would you want to use inside TLS, for example. The particular curve that we're using in SALT is a curve of mine from 10 years ago called curve 25519, which still seems to be state of the art. Some more decisions, instead of using AES, use another cipher, Salsa 20. So this is something which is a few years newer than AES, and it was one of the members of the portfolio of the eStream competition carried out in Europe for 2004 to 2008. And again, main reason to switch from AES to another cipher, it's not that AES is something where it's crumbled and the mathematical security is a problem, but it's a real pain to implement, and it's not really designed for being as secure as possible. NIST's comments when they were choosing AES, there were a few different candidates left in the AES competition years ago. And they said, well, here's this candidate, Serpent, which is really high security margin, really confident in that one. And then there's this other thing, Rheindal, which is, it's got some security margin, looks okay, and it's faster. And they chose the faster one for AES. Well, we go for more conservative stuff because we want things that will last for many, many years and that we're not going to have to do any emergency upgrades. Similarly, instead of using HMAC, use Poly 1305. So this is something where the Poly 1305 component of the system is information theoretically secure. That means that that part has an absolute mathematical proof that it won't have to be upgraded. There's other things which attackers can try to break, but the information theoretically secure parts are things that there's no risk. And then the last thing here on the list is the choice of signature algorithm. Instead of using EC DSA, we're using ED DSA. And then we have maybe some time.
Well, we put a bunch of slides towards the end. Uh-oh. Okay. So when you listen to people about what signature system to use, say for TLS, even for fairly recent designs, they mentioned, yes, you want to have ECC, some Diffie-Hellman in order to get forward secrecy, but many people still prefer RSA signatures over elliptic curve signatures with the argument that in general DSA, so the defined field version, or ECDSA are very, very touchy. And then they point to the PlayStation disaster, which we had on the slide before, and say, well, if you ever get your randomness wrong, then your long-term key is leaked. Now, the problem with that is, yes, the way that DSA and ECDSA were specified has this problem. Luckily, a year and a half ago, NIST updated the specification, and it's no longer saying that you must use randomness. So you can have pseudo-randomness, you can use something which is hashed, so that would avoid having the PlayStation disaster problem. Now, when we sat down and designed ED-DSA, we went back to where signatures come from, so general, plain, algo-mal signatures were like the first signatures to come up after, well, based on discrete logs. And what you need basically is you need somewhere to put the hash of the message, you need somewhere where you're putting your secret key, so that's now written here as the exponents, then you have your base point and you have your public key, and then there's the signature equation. Now, in here, the R is coming from the randomness and it appears in the top and in the bottom. And then this is here the verification equation. Now, going through this, soon after there was several improvements by Schnorr saying, hey, look, here's nice things you can do. You can make it shorter, you can make it faster, you can make it easier on the hash function. For instance, you can avoid having the problem that if anybody has a collision attack, this thing where the two messages hash to the same value, you can avoid doing this by hashing in something which is not under the control of the attacker. So you plug in not just the message here, but you plug in also the randomness. That totally protects you against this collision attacks. And then, well, a bunch of other things. Now the problem why this is not in DSA, at least the only version that we know of, it's nice, it's secure, it's faster, but it got patented. So DSA, ECDSA as written do not use any of these improvements. Now the good news is time has gone down and the patent has expired. So that's what happens with patent in cryptography. It's not that people pay the royalties, it just means, well, what we see online is less secure. So we did our research after 2008, and then I hand over to Dan to show some of the nice features we did.
Wow. Okay, so this last slide here, the EdDSA system, just an example of the kinds of choices that we make in the SALT library, is using the state-of-the-art, carefully studied elliptic curve technology with all the improvements that theoreticians were talking about, but that weren't deployed because of these patents. There's various buzzwords here, which people who saw our talk last year would recognize some of these, like Edwards curves. And the result of making the right choices is that we end up with the performance being better than any ECDSA implementation. The side channel, the timing attack protection is better. It's just easier to implement, much easier to implement securely than ECDSA is. There's no weird cases that are hard to test for. Everything is easy to test for, and we do tons and tons of tests. And then there's all sorts of extra features which protect us just in case and add some extra speed features just in case, like the batching that I mentioned. Extra security is, well, we choose a hash function which is twice as long as it would need to be for what we think the security has to be, but hey, it's something which is really cheap to do in this context, so we might as well make it safe. And then the very last comment is that by not using randomness at this point, remember, we try to avoid randomness if we don't need it, by having the R's in all these equations being generated in a deterministic way, we make sure that all of that DSA trouble with people screwing up how they choose a randomness for each signature, that just cannot happen. And it's the protection against it is something that we can test for. I mean, it's obvious from the code, but you can also totally audit it, and we're absolutely confident that that problem is gone. That's it. Thank you for your attention.
All right, we're being signaled from our session chair that we should ask for questions. Are there any questions? Please shout. Yes?
So, I'm curious if like TLS is in scope at all for any of this? Like actually adding some basic TLS support to SALT?
Okay, so the question was whether TLS is in scope for any of this. Our perspective for the crypto library is that we try to deal with all the problems at this layer and make something which is suitable for use in, for instance, on the left slide there, suitable for use in protocols like Quick and Minimal, and people are thinking, what should TLS do? And then that's certainly an important part of the cryptographic picture, and it's something which has to be gotten right, has to be audited, and there's all sorts of similar questions that you can ask about doing that layer right. But we're not doing that within the cryptographic part of the networking and cryptography library. That's what NaCl stands for, and the networking and part is saying that we will be moving up into that area, but so far everything that we have, I mean, what you'll find online is the cryptographic part, and that's something where we're leaving to other people, the higher layer.
And for Minimal in particular, there should be a Linux version out real soon, John tells us. John, if you're watching this? There was some question?
Yes, two quick questions. One is, on the underlying crypto that you're using, what do you think is most likely to fall down or fall out of favor in the next 10, 20, 30 years? And the second question is, what guarantee or what proof is there that there's no defect in the implementation?
Okay, let me get the first question first. So the first question was, what of these primitives is most likely to break in the next X years, where his values for X were 10, 20, and 30? For going for large values of years, the biggest threat I see, which also means that I don't see any short-term threat, is quantum computers. So this is based on elliptic curve cryptography, and elliptic curve cryptography, just like RSA, will be broken by quantum computers. So there are polynomial time attacks against the public key crypto that we have in here with a quantum computer. So we are working on getting other primitives. So the one reason why we see to upgrade the primitives for salt is to have a post-quantum version of it. The problem with that is, at the moment, there are not really the replacements you would like to use. We're pretty sure what is secure, but they're very inconveniently big. The second question,
Okay, yeah, so second question was, how sure are we about the quality of the implementation? Is that a fair statement of it? Yeah, so there's a number of things that we do to try to make sure that the implementation is absolutely going to work, going to provide the security that we promise. So one of them, first of all, is manual audits. Now, that's something where it's a scalability problem to try to scrape up enough time for competent auditing, but it can be done when you have code that doesn't have unnecessary options, and when you compress everything down to, say, 100 tweets, then suddenly that's a size where you can imagine just absolutely going through every single byte of that and knowing exactly what it does and being confident that it does the right thing. Now, I don't mean to suggest that TweetSalt is fully audited yet, but at least it's something which is feasible and we are working on. So if you follow the TweetSalt links, then you will find some partial audits with computer formal verification. So actually having the computer formally verify certain properties, it's not everything yet, but TweetSalt will be, it is the first human auditable, and it will be the first computer audited cryptographic library. Now, beyond that, getting to the full, very fast SALT library, there's some extra problems with verifying the fast assembly language implementations of things, but we're working on that as well. And at least this is something where I can look into the future and say, yeah, it's definitely a problem, working on it, and it's a much bigger problem for all the other libraries. At least if you keep everything simple and small, then you have a hope of getting these problems fixed.
all right, there was a stop sign in the back there. We're still here for the rest of the conference, so if you have more questions, we couldn't answer them right now, please find us, and thank you for your attention.